Have you ever wondered what existed before the universe? Before the stars, before the planets, and before Earth was possible, there was a moment in cosmic history that still challenges everything we think we know. We call it the Big Bang. But the Big Bang was not an explosion inside empty space. It was the expansion of space itself. That means the real question is not just what happened after the Big Bang. The real question is what came before it. Was there another universe? Was there an earlier reality? Or did time itself begin there? For thousands of years, people have looked up at the sky and asked where everything came from. Today, science asks the same question with telescopes, mathematics, and evidence from the farthest parts of the universe. The universe was once much hotter, much denser, and much smaller than it is today. But when we try to go all the way back to the start, our current understanding begins to break down. The Big Bang Theory explains a huge amount about the early universe. It explains expansion, cooling, the first particles, atoms, stars, and galaxies. But it may not explain the absolute beginning of everything. To understand why, imagine rewinding a movie of the universe. At first, the galaxies move closer together. Space gets smaller. Heat increases. Matter becomes more compressed. Keep rewinding far enough and you reach a state so extreme that our usual laws of physics stop working properly. Scientists call this a singularity. But many physicists believe that this does not mean nature truly contains an impossible point of infinite density. It may simply mean our current theories are incomplete. General relativity works incredibly well for planets, stars, galaxies, and black holes. Quantum mechanics works incredibly well for atoms and particles. But at the beginning of the universe, both theories must work together. And that is something we still do not fully understand. So one possibility is that time itself began with the Big Bang. In that case, asking what came before it may be like asking what is north of the North Pole. The question sounds natural, but the answer may not exist in the way we expect. If time began with the universe, then there may have been no earlier moment at all. If time began with the universe, then the question of what came before the Big Bang may not work the way our minds expect. But that does not mean science has no clues. In fact, the universe has left behind several powerful traces that help us understand its earliest history. One of the most important clues is the expansion of space. When scientists observe distant galaxies, they see that those galaxies are moving away from us. Even more interesting, the farther away a galaxy is, the faster it appears to move away. This was one of the first signs that the universe is not static. It is expanding. That discovery changed everything. If the universe is expanding now, then it must have been much smaller in the past. If we keep running that idea backward, we reach a time when the universe was extremely hot, extremely dense, and incredibly compact. That early state is what we call the hot Big Bang. But the hot Big Bang is not just an idea. It is supported by observations. One of the strongest pieces of evidence is the cosmic microwave background. This is a faint glow that comes from every direction in space. It is not light from stars. It is ancient radiation left over from when the universe was still young. Long ago, the universe was so hot that light could not travel freely. Matter and radiation were constantly interacting. The universe was like a glowing fog. As it expanded, it cooled. Eventually, atoms formed, and light was finally able to move through space without being trapped. That leftover light is still with us today. We detect it as a weak microwave signal, and it tells us a great deal about the early universe. The cosmic microwave background is often described as the baby picture of the cosmos. It shows tiny differences in temperature, and those small differences mattered a lot. Over billions of years, gravity used those tiny variations as seeds for structure. Regions that were slightly denser pulled in more matter. Gas collected. Stars formed. Galaxies formed. Entire clusters of galaxies grew out of those small early fluctuations. Another clue comes from the amount of hydrogen and helium in the universe. In the first few minutes after the Big Bang, the universe was hot enough for the first light elements to form. The predicted amounts of hydrogen and helium from Big Bang theory match what astronomers actually observe. That is one more reason scientists take the model seriously. Still, the biggest question remains. Did the universe begin from an absolute beginning, or was the hot Big Bang only one chapter in a larger story? Some theories say there may have been a previous universe. In those models, a prior cosmos may have collapsed before ours expanded. Other theories suggest a cyclic universe, where expansion and collapse repeat over and over again. In that picture, the Big Bang is not the first event ever. It is simply one transition in an endless cosmic cycle. There are also ideas that our universe is only one bubble in a much larger multiverse. If that is true, then what we call the Big Bang would be the beginning of our local region, not the beginning of all reality. These ideas are fascinating, but none of them has been proven. At this point, science is very good at describing the universe after the first fractions of a second. It is very good at tracing the universe back to a hot, dense past. But the very first instant remains hidden behind the limits of our current theories. That is why many physicists say we need a theory of quantum gravity. General relativity handles gravity and large-scale structure beautifully. Quantum physics handles particles and microscopic behavior beautifully. But the earliest universe demands both at once. Until we have a theory that combines them completely, the ultimate beginning will remain uncertain. And so the mystery deepens. The universe clearly has a history. It clearly passed through an early hot phase. But whether that phase was the beginning of everything is still unknown. That is the real edge of modern cosmology. Not a wall of ignorance, but a frontier where our best ideas still reach their limit. If the universe had an early hot beginning, then one of the biggest questions is what that beginning actually looked like. To answer that, scientists study not just the universe today, but the universe as it was billions of years ago. Because light takes time to travel, looking far away also means looking back in time. The farther we look, the earlier the universe we see. This is one of the most powerful ideas in cosmology. Every galaxy is like a message from the past. Every bit of light that reaches us from a distant object carries information about an earlier stage of the universe. That is why telescopes are not just tools for seeing space. They are time machines in a very real sense. When astronomers first realized that distant galaxies were moving away from us, it revealed something remarkable. The universe is not standing still, it is expanding. And if expansion is happening now, then in the past everything must have been closer together. That means the entire observable universe was once compressed into a much smaller volume. At first, this sounds impossible. How could everything fit into such a tiny state? But in physics, small does not mean simple. The early universe was not a little version of the universe we see today. It was a completely different environment. Temperature, density, and energy were far beyond anything we can create on Earth. As the universe expanded, it cooled. That cooling allowed particles to form, then atoms, then stars, and eventually galaxies. The early universe was not filled with empty space the way we think of space now. It was a hot plasma of radiation and matter, constantly interacting. Light could not travel freely until the universe cooled enough for atoms to form. Only then could photons move through space without being absorbed again and again. That moment left behind the cosmic microwave background, one of the strongest signs that the Big Bang model is correct. But the background radiation does more than prove the universe was hot. It also shows us that the early universe was nearly uniform, with tiny differences in temperature. Those tiny differences became the seeds of all large-scale structure later on. Gravity took over from there. Regions that were slightly denser began pulling in more matter. Over time, these regions grew into galaxies, galaxy clusters, and the web-like structure of the cosmos. So the universe we see today is the result of a long process that began with very small differences in the early state. Still, all of this tells us what happened after the beginning started. It does not fully explain what created the beginning itself. That is why many scientists keep returning to the idea that our current laws may not be enough. General relativity tells us how gravity shapes space and time. Quantum mechanics tells us how the smallest things behave. But near the very beginning, both matter and spacetime were pushed to extremes. That is where the two theories must be unified, and that unification has not yet been completed. Without a full theory of quantum gravity, the earliest instant remains uncertain. We can trace the universe far back. We can describe its heat, density, and expansion. But eventually, the equations begin to lose reliability. That does not mean we know nothing. It means we know a great deal, but not everything. Some researchers believe the earliest state may have been a bounce instead of a beginning. In that idea, a previous universe may have contracted, reached an extreme point, and then rebounded into expansion. Our Big Bang would then be the rebound, not the first moment of existence. Others think the universe may go through endless cycles of growth and collapse. In that case, the beginning we talk about may simply be one turn in a larger cosmic pattern. Another idea is that inflation played a major role. Inflation suggests the universe underwent a brief period of extremely rapid expansion very early in its history. This helped smooth out the universe and explain why it looks so uniform on large scales. Inflation also helps explain how tiny quantum fluctuations were stretched into the structures that later became galaxies. But even inflation raises more questions. What caused inflation? Did it have a beginning? Did it happen only once? Or is it part of a bigger process? The important point is that the universe may be deeper, stranger, and more layered than our current picture fully captures. What looks like a beginning to us may actually be a transition. The word before seems simple in everyday life, but cosmology makes it complicated. We use the word naturally because our lives are built around time. Morning comes before afternoon. Childhood comes before adulthood. One event leads to another in a clear sequence. But when we talk about the universe itself, that sequence may not work in the usual way. Einstein's relativity changed the way we think about space and time. It showed that time is not separate from the universe. It is woven together with space into a single structure called spacetime. That means time is not just a background clock running outside reality. Time is part of reality itself. If the universe began, then spacetime may have begun too. This leads to one of the strangest ideas in modern science. If time began with the universe, then asking what happened before the Big Bang may be like asking what lies north of the North Pole. The question sounds normal, but the direction stops making sense once you reach the edge. There may simply be no before in the ordinary sense. That is difficult for us because our brains are trained to think in terms of causes and effects. A seed causes a tree, a match causes fire, a builder causes a house. We are constantly looking for what came first, so it is natural to ask what caused the universe, but causation itself depends on time. A cause has to come before an effect. If time itself begins with the universe, then the idea of a cause may not work the same way at the cosmic origin. This does not mean science is saying the universe magically appeared without explanation. It means the explanation may require a deeper kind of physics than the one we currently have. There is also confusion around the word nothing. In everyday speech, nothing means total emptiness. No space, no time, no matter, no energy, no rules, and no possibilities. But in physics, nothing often means something much less absolute. A quantum vacuum may look empty, but it is not truly nothing. It can contain fluctuating fields and physical structure. So when scientists suggest that a universe might emerge from a quantum state, they are not always talking about philosophical nothingness. This matters because many popular ideas about the beginning of the universe are oversimplified. People often imagine one clean answer, like a switch turning on reality. But the actual situation may be much more subtle. The universe could have emerged from a quantum process, a bounce, a transition, or some kind of pre-existing state we do not yet understand. What we do know is that the universe had an early hot phase. We know it expanded. We know it cooled. We know the first particles, atoms, stars, and galaxies formed over time. But whether all of that began from absolute nothing, from a previous cosmos, or from a deeper reality is still unknown. This is why cosmology remains such a powerful field. It is not just about stars and galaxies. It is about existence itself. Every new answer opens another question. Every discovery reveals a deeper layer. The edge of knowledge is not a dead end. It is the place where the biggest questions live. If the universe may not have started from nothing in the ordinary sense, then what are the leading possibilities for its origin? Scientists have explored several major ideas, and each one tries to solve the same mystery from a different angle. One possibility is that our universe came from a previous universe. In this view, the Big Bang was not the absolute beginning. Instead, it was a transition from one state to another. A previous universe may have expanded, slowed down, and collapsed. At some extreme point, something may have happened that led to a new expansion. Our universe would then be the result of that transformation. This is sometimes called a bouncing universe idea. It avoids the problem of a true beginning by replacing it with a cycle. Rather than asking how something came from nothing, it asks how one phase of reality changed into another. This is appealing because it gives the cosmos a kind of continuity, but it also raises hard questions. If one universe collapsed before ours, what caused the collapse? If this is true, then the Big Bang is not the beginning of everything. It is the beginning of our local region. This is a fascinating idea because it changes the scale of the question. Instead of asking what came before our universe, we may need to ask what exists beyond our observable patch of reality. But eternal inflation is still a theoretical idea, not a confirmed fact. It is elegant, but it remains unproven. Then there is the possibility of a multiverse. This is a broader idea than inflation. It suggests that reality may contain many universes with different physical properties. Some could be similar to ours. Others could be wildly different. In such a picture, our universe would not be alone. It would be one chapter in a much larger collection of cosmic histories. The multiverse is exciting, but it is also controversial. The challenge is that other universes may be impossible to observe directly. Science depends on testable predictions, and if a theory cannot be tested, it becomes harder to confirm. That does not mean it is wrong. It means the evidence is not yet in. Another line of thought comes from quantum cosmology. Some models suggest the universe could arise through a quantum event. In those models, spacetime itself may emerge from a more fundamental quantum state. That would mean the beginning of the universe was not a giant explosion in space. It was the birth of space itself from a deeper physical process. These ideas are very different, but they all point in the same direction. The universe may not be as simple as a single starting point. The beginning may be part of a larger process, or a transformation, or a boundary we have not yet learned how to cross in theory. For now, we have no final answer, but we do have a clear lesson. The universe is not easily explained by ordinary intuition. It asks us to think beyond the limits of everyday time, everyday space, and everyday cause and effect. That is what makes the question so powerful. The more we ask about the beginning, the more we discover how much there still is to understand. If the Big Bang was not the whole story, then what comes next in our search for the origin of the universe is the possibility that the beginning we talk about was really a transition. That idea appears again and again in modern cosmology because the universe seems to invite us to think beyond a single starting point. One reason scientists do this is that the laws we know today work beautifully in many situations, but not all. When we look at the motion of planets, the behavior of stars, the bending of light, and the life cycle of galaxies, general relativity gives us an elegant framework. When we look at atoms, particles, and the strange behavior of matter at tiny scales, quantum mechanics gives us a different but equally successful framework. The problem comes at the earliest moment of the universe, when both gravity and quantum behavior must matter at the same time. That is where our current picture becomes incomplete. Because of this, some researchers think the universe may have passed through a bounce. In a bounce model, a previous universe could have been contracting for an unimaginably long time. As it shrank, density and temperature would increase until some unknown physical effect stopped the collapse. At that point, instead of ending in an irreversible singularity, the universe would rebound and begin expanding again. Our Big Bang would then be the result of that rebound. This idea is attractive because it avoids a true absolute beginning. It replaces the question, how did something come from nothing, with a different question. How did one state of reality become another? That is still a profound question, but it feels more natural to many scientists because it suggests continuity. Reality does not need to appear from nowhere. It only changes form. The bounce idea is not the only possible alternative. Another major concept is eternal inflation. Inflation refers to an extremely rapid period of expansion in the very early universe. It was proposed to explain why the universe looks so smooth and uniform on large scales, even though it contains tiny irregularities that later grew into galaxies. If inflation happened, it would have stretched the early universe faster than ordinary expansion could ever do. That smooths out the fabric of space and helps explain the structure we observe today. Some versions of inflation go further. They suggest inflation may not have ended everywhere at once. Instead, it may continue in some parts of a larger reality while stopping in others. If that is true, then our universe could be one bubble among many. Each bubble universe could form when inflation ends locally. Our Big Bang would not be the birth of all existence. It would be the birth of our own observable region. This idea is fascinating because it makes the universe much bigger than what we can directly see. It also changes the meaning of origin. Instead of asking where everything came from, we might ask where our region came from and what kind of larger background produced it. That is a very different question, and it pushes cosmology into even more speculative territory. There is also the multiverse idea, which overlaps with inflation but can be broader than it. In a multiverse picture, reality may contain many separate universes with different physical conditions. Some may share laws similar to ours. Others may have very different constants, particle types, or forms of matter. In that kind of framework, our universe is not unique in the deepest sense. It is simply one instance among many possible cosmic histories. This possibility is exciting because it offers a way to explain why our universe has the properties it does. Maybe the conditions that allow stars, chemistry, and life are not guaranteed everywhere, but only in certain regions. We happen to live in one of those regions. Still, the multiverse remains difficult to test. Science depends on evidence, and if other universes cannot be observed, then the idea remains hypothetical. Another line of thought comes from quantum cosmology. This field tries to apply quantum ideas directly to the universe as a whole. In some models, spacetime itself is not fundamental. Instead, it emerges from a deeper layer of physics. If that is true, then the earliest universe may not have been a place filled with pre-existing space. Space itself may have emerged gradually, or in a sudden quantum event from a more basic structure. That idea is hard to imagine because we naturally think of space as the stage on which everything happens. But perhaps the stage is part of the performance. Perhaps space is not the container of reality, but one of its results. What all of these ideas share is a willingness to accept that the beginning may not be a simple point in time. It may be a process, a transition, a change of state, or even a limit on what our current language can describe. We are used to beginnings having a clear first moment, but the universe may not obey that expectation. And that is where the mystery becomes beautiful. The more scientists explore the origin of the cosmos, the more they discover that the universe is not just old. It is layered. It has history. It may have prehistory. And the thing we call the beginning may be only the first doorway we can currently see. To understand why the origin of the universe remains so difficult, it helps to return to the strange relationship between space and time. In everyday life, we treat time as if it moves in one direction while space simply sits there. We think of space as the arena and time as the clock, but modern physics does not let us separate them so easily. Space and time are linked together in spacetime, and the behavior of one affects the behavior of the other. This becomes especially important near the beginning of the universe. When the cosmos was extremely hot and dense, distances were tiny and conditions were extreme. In that environment, the neat separation between space and time starts to break down. If spacetime itself was evolving, then asking what happened before, the earliest moment may depend on whether time even existed in the same way it does now. This sounds abstract, but it is actually one of the most practical problems in cosmology. We can observe the universe as it was when it was already millions or billions of years old. We can study the cosmic microwave background, galaxy formation, and the expansion of space. But we cannot directly observe the very first instant because our current theories lose precision there. That is the boundary where physics becomes incomplete. One reason the problem is so hard is that gravity becomes overwhelmingly important when everything is squeezed into a tiny region. General relativity describes gravity as the curvature of spacetime. It works extremely well for large-scale phenomena. But when quantum effects become important, spacetime itself may fluctuate. That means the smooth picture of the universe begins to fail. We may need a deeper theory that combines gravity with quantum behavior in a single framework. Physicists often call this missing framework quantum gravity. It is not yet fully developed in a confirmed form. Many approaches exist, but no final experimental answer has settled the question. Until then, the very earliest universe stays hidden behind a curtain of uncertainty. We know the curtain is there because our equations stop giving reliable answers at the smallest scales and earliest times. This does not make the search useless. In fact, it makes it more important. Every clue we find helps narrow the possibilities. For example, the cosmic microwave background gives us information about the universe when it was only about 380,000 years old. That may sound incredibly early, but it is far after the first instant. The universe already had structure by then. To go earlier, we need additional evidence and better theories. One approach is to study how tiny fluctuations in the early universe grew into the large structures we see today. If the universe started in a nearly uniform state, then small quantum fluctuations could have been stretched by inflation, and turned into the seeds of galaxies. That gives scientists a bridge between the very small and the very large. It connects quantum behavior with cosmic structure. But again, the deeper question remains. Why did the universe begin in such a state at all? This is where the word begin itself becomes suspect. A beginning usually implies that something did not exist and then came into existence. But in cosmology, the universe may not have appeared the way a machine starts up. Instead, it may have transitioned from one physical condition to another. In that case, the beginning we talk about is only a limit of our perspective, not necessarily the absolute start of existence. There is also a philosophical side to this. Human beings naturally want the first cause. We want a final answer. We want to know what started everything. But the universe may not offer that in the form we expect. The laws of nature may describe transitions, relations, and structures, but not always a simple first push. The cosmos may be less like a machine someone turned on and more like a process that has no easy first page. And yet the search continues because the universe keeps giving us clues. Every observation teaches us that reality is more surprising than common sense suggests. Light reveals the past. Gravity shapes time. Space expands. Matter organizes. Small fluctuations become galaxies. What seems simple becomes layered. What seems distant becomes connected. So when we ask about the beginning of the universe, we are not just asking a scientific question. We are asking a question about the nature of reality itself. Does every story need a first sentence, or can the story begin inside an ongoing process? That is the deeper mystery at the edge of cosmology. One of the most important lessons from modern cosmology is that the universe looks simple from far away, but becomes complex the closer we examine it. On large scales, it appears smooth and expansive. On smaller scales, it is full of structure, variation, and history. That pattern matters because it tells us the early universe was not just hot and dense. It was also finely balanced. If the universe had expanded too quickly, matter may never have had time to form stars and galaxies. If it had expanded too slowly, gravity could have caused it to collapse again too soon. If the initial conditions had been slightly different, the universe might look completely unlike the one we inhabit. This sensitivity is one reason cosmologists study the origin so carefully. The early universe contains the explanation for everything that came later. This brings us back to inflation, one of the most influential ideas in cosmology. Inflation proposes that the early universe underwent a brief phase of extremely rapid expansion. During that period, the size of the universe increased enormously in a tiny fraction of a second. This helps explain why the universe appears so uniform even though distant regions should not have had time to communicate with each other under ordinary expansion. Inflation also helps explain the origin of structure. Tiny quantum fluctuations during inflation could have been stretched across cosmic distances. Later, those tiny differences would become the seeds of galaxies and clusters. In that sense, inflation connects the microscopic world of quantum mechanics with the grand scale of the cosmos. It gives us a mechanism by which tiny random variations became the architecture of the universe. But inflation does not solve everything. It raises new questions. What drove inflation? What caused it to stop? Was it a one-time event, or does it continue in some form elsewhere? If inflation is eternal in some regions, then it could constantly generate new bubble universes. That would mean our universe is only one small part of a much larger inflating background. This idea is both exciting and unsettling. Exciting because it widens the horizon of what might exist. Unsettling because it stretches science beyond easy observation. If other universes are forever out of reach, how can we know they are real? That is the central problem. A beautiful idea is not enough. Science needs contact with evidence. This is why cosmologists often return to the observable universe. They analyze the cosmic microwave background with extreme precision. They study the distribution of galaxies. They measure how fast the universe is expanding. They compare theory with data. Every small mismatch can reveal something important. Sometimes it confirms a theory. Sometimes it rules one out. Either way, the universe is the final judge. The oldest light we can see still tells us that the universe had a hot beginning. The pattern of that light tells us there were tiny variations. The abundance of light elements tells us the first minutes were governed by known physical processes. All of this strengthens the Big Bang model. But the model itself may only describe the early chapters, not the opening line. That distinction matters. A theory can be successful without being complete. The Big Bang model is one of the greatest scientific achievements because it explains so much. But it may be part of a larger theory waiting to be discovered. Perhaps the universe is not one event, but a series of transformations. Perhaps there was a prehistory we have not yet learned to decode. The deeper we go, the more the origin becomes less like a dot and more like a boundary. It is the edge where our current language, our current mathematics, and our current imagination begin to strain. And that strain is not failure. It is progress. It shows we are reaching the limits of what we know and preparing to go beyond them. The question of what happened before the Big Bang continues to inspire both scientific and philosophical thinking because it sits at the edge of explanation. It is not just about origins in a technical sense. It is about whether reality itself has a first moment, or whether what we call a first moment is only the beginning of a chapter within a larger whole. Some scientists hope that future discoveries will settle this question. Better measurements, better telescopes, better particle experiments, and better mathematical frameworks may eventually give us a more complete story. That story might show that the Big Bang was a true beginning, or it might reveal that something came before it in a form we do not yet understand. One possible future path is a complete theory of quantum gravity. If gravity and quantum mechanics can be unified, then the earliest universe may become more accessible to calculation. We might then understand what happened at scales where spacetime itself was not smooth. This would be a major breakthrough because it would allow us to explore conditions that current physics cannot fully describe. Another future path is more observational. Scientists may detect new patterns in the cosmic microwave background or in gravitational waves that carry information from the universe's earliest moments. Gravitational waves are ripples in spacetime itself, and they may preserve hints of events from extremely early times. If we can detect such traces, we may learn more about inflation, bouncing models, or other origins. There is also the possibility that the answer will not be one neat theory, but a combination of ideas. The universe may have features of inflation, features of quantum emergence, and features of a deeper underlying process. Nature does not always choose the simplest story from our point of view. It chooses the story that actually happened. That is why the search is so exciting. It is not only a hunt for facts. It is a test of our deepest assumptions. We assume that time is ordinary, but it may not be. We assume that cause and effect always behave the same way, but at the cosmic origin they may not. We assume the universe must have a first moment in the way a human story does, but perhaps it does not. Still, even if science never finds a final answer in the way people hope, the search itself has already revealed something profound. It has shown that the universe is not a simple machine placed before us to be read at a glance. It is a rich and evolving reality with layers that stretch far beyond daily intuition. Each new discovery tells us that our picture is partial, but partial knowledge can still be powerful. It can still explain a great deal. It can still point us toward deeper truth. The early universe tells a story of heat, density, expansion, cooling, structure, and time. From a nearly uniform beginning, stars and galaxies emerged. From simple particles, atoms formed. From atoms, chemistry became possible. From chemistry, life eventually arose on one small planet. That chain is remarkable on its own. Even without knowing the ultimate first cause, we can see how much the universe has accomplished. So perhaps the biggest lesson is not just about where the universe came from. It is about how reality transforms. The cosmos may not be a frozen object. It may be an unfolding process. If that is true, then origin is not a single point, but a continuing relationship between what was, what is, and what becomes. That idea keeps the mystery alive without making it hopeless. It reminds us that not knowing is not the end of understanding. It is often the beginning of deeper inquiry. And the universe, with all its age and scale and silence, still leaves room for wonder. In the end, the question of what existed before the universe may not have one simple answer. It may depend on which model of reality turns out to be correct, or whether future physics reveals something entirely new. But even without a final answer, we have learned something meaningful about the universe and about ourselves. We have learned that the universe had a hot and dense early state. We have learned that space is expanding. We have learned that the cosmic microwave background is an ancient echo of that early time. We have learned that the first light elements formed in ways that match observation. These are not guesses. They are among the strongest conclusions in modern science. We have also learned that the laws we use today may not be enough to describe the deepest origin. General relativity and quantum mechanics are each successful in their own domain, yet the earliest universe asks them to work together. That challenge has not been solved completely, so the boundary remains open. And maybe that is the most honest place to be. Science does not need to pretend certainty where certainty does not yet exist. It can say with confidence what the evidence shows. It can also say with equal honesty where the evidence ends. The origin of the universe belongs in that second category for now. We can see its outline, we can trace its effects. But the first instant, or the question of whether there even was a first instant in the usual sense, still stands beyond our current reach. That does not make the question meaningless. It makes it one of the most important questions we can ask. It forces us to examine what we mean by beginning, by time, by space, and by cause. It asks whether the universe is something that started, or something that transformed, or something that was always part of a larger reality. It asks whether our familiar logic is enough to describe the cosmos at its deepest level. In that sense, the mystery of the universe's origin is not a weakness in science. It is one of its greatest strengths. It shows that human knowledge is capable of reaching extraordinary heights while still admitting the limits of what we know. That humility is essential. It keeps the search honest. It keeps the curiosity alive. The universe may have begun with a big bang, or with a bounce, or with a quantum emergence, or as part of a multiverse, or through a process we have not yet imagined. Whatever the answer turns out to be, it will likely change our understanding of reality in a deep way. And when that answer comes, it will not close the story. It will open another chapter. For now, we live in the most interesting place of all, the frontier between what is known and what is still hidden. The sky above us is not just a display of stars. It is a record of cosmic history. Every distant galaxy, every faint radiation, every trace of structure carries evidence from the past. We are reading the universe one clue at a time, and maybe that is enough to keep us searching. Because the greatest discoveries often begin with a question that refuses to disappear. What was before the universe? What started everything? What deeper reality gave rise to space, time, matter, and light? We do not yet know. But the fact that we can ask the question at all is a sign of how far human thought has come. The universe is still speaking. We are still listening.